For more videos, visit forthesakeofeducation.com. Alright guys, let's do this problem which says determine the tension developed on the cables AB and AC and the force developed along the strut AD for equilibrium. So look at the tensions right here at A. You got a tension going up here, you got a tension going up here, this one's obviously going up and this one's going down. So this is basically our free body diagram. Now the first thing that we need to do in this kind of problems, this is a technique guys. Look, what you got to do is you got to find univectors aiming in all these directions. So you need a univector here with a magnitude of 1, a univector here, a univector here, and a univector here. And when you have all the univectors, the problem becomes much more obvious and simple. So remember, technique is univectors. Now you remember from chapter 2, you got to find the univectors, find all the points involved first. That's my technique. So A sits at 0 in the I, plus 6 in the J, plus 2.5 in the K. B sits at negative 2 in the I, plus 0 in the J, plus 4 in the K. C sits at 2 in the I, plus 0 in the J, plus 5.5 in the K. And D sits at 0, 0, 0, plus 0, plus J, plus 0 in the K. Now we have all the points involved. Time to find some univectors. So let's start with the univector that goes from A to B. We gotta find AB first. AB is B minus A, which is negative 2I minus 6J plus 1.5K. The magnitude of this vector is equal to the square root of x squared plus y component squared plus c component squared, and it's equal to 6.5. Now the univector along AB is equal to this vector AB divided by its magnitude. So you basically are going to divide this whole vector divided by the magnitude, and you're going to get the univector AB, which comes out to be negative 0.308 in the I, it's a negative there, minus 0.923 in the J, plus 0.231 in the K. A little tip, you got to be as neat as possible when you're doing these problems, because it's going to be a lot of numbers in your paper, and if you forget a little negative sign or something at the beginning, then you're going to have to start the exercise all over when you get the wrong answer. So try to be as neat as possible. Well, we have a univector AB. One more step that you need to do is you need to remember the force AC, this tension right here, tension AB, is going to be equal to this tension multiplied by this univector. So we're going to use that later. For now, let's just keep finding more univectors. So let's find AC now. AC is C minus A, which is equal to 2I. I'm going to move a little quicker, okay guys? Minus 6J plus 3K. Magnitude of AC, find the same way as the other one, is 7 exactly. So univector AC should come out to be 0.286 in the I, minus 0.857 in the J, plus 0.429 in the K. We got this other tension now. Then we need the one going down for the crate, and that one's really easy. The univector going down for the crate, let's call this point E. So we're gonna call AE, right? The univector AE is equal to minus 1 in the K, because it's going down on the C axis, so it's just minus 1 in the K. You don't need to calculate anything. And then last but not least, we need univector dA, so we found dA. Remember, it goes from D to A, not from A to D. Since they're all starting AB, AC, AE, You might think, hey, A to D. No, it's backwards because the force is going towards A, not away from A. So dA is equal to A minus D, and it is equal to A because D is at the origin, and A is equal to 0 in the I plus 6 in the J plus 2.5 in the K. The magnitude of dA is equal to 6.5, and unit vector dA is equal to 0 in the I plus 0.923 in the J plus 0.385 in the K. Now I'm going to be working with the unit vectors, so I'm going to put them in squares so they're easy to find in my paper. That's a good habit too. Whenever you have an important number that you know you're going to use, you put it in a square and you can go back to it really quick further down the exercise. So I have, oh, I'm missing one right here. We got your 4 unit vectors for the four tension vectors or force vectors in case of the stick acting on A. Now this problem becomes very simple. You know always that the sum of the forces in statics is equal to 0, no matter what way they're aiming, right? And you know that the tension of AB is equal to T, the magnitude of this tension, times the unit vector of AB. And this applies to all of them. Tension of AC is equal to the tension of AC times the unit vector AC. The tension, the force dA is a force because it's a stick, it's not a tension, is equal to the magnitude of this force times the unit vector that goes from D to A, and the tension of AE, the one holding the crate, is equal to UAE times the magnitude TAE. Okay, you know this, right? So what you're going to do is you're going to multiply the magnitude times each of these unit vectors. I'm going to turn the page. New layer. Okay, so I'm going to multiply the unit vectors by their respective tensions to get the Cartesian vector form of all these forces, and you're going to see why this problem becomes much easier. So take unit vector AB. Tension AB, which like I said is equal to the magnitude of the tension times the unit vector AB, is equal to negative 0.308. Let's call it AB. Let's not write T for all of them. AB minus 0.923 AB plus 0.231 AB. Tension AC is equal to, you see what I'm doing? I'm rewriting the unit vector multiplied by the magnitude of what I'm looking for. This is AC, so it's 0.286. I'm sorry, I forgot the unit vectors in the I, in the J, and in the K. 0.286 AC in the I minus 0.857 AC in the J plus 0.429 AC in the K. Now we got the tension, not the tension, sorry, the force dA. Now the force that goes from D to A is nothing because it's 0 in the, let me actually write 0, so 0 in the I times plus 0.923 dA in the J plus 0.385 dA in the K. And the last one is the tension AD. Remember the one going down here, this is D. I called it D, it wasn't on the exercise. E, I'm sorry. E, tension AE is the one being held by the weight, and remember it's -1 in the case, so this is 0 in the J, minus 1 in the K, but you gotta multiply by the magnitude of the tension AE, which is 400 pounds, because it's holding a 400-pound crate, so it's minus 400 in the K. Now the problem becomes very simple, because you know that the sum of the forces is equal to 0. So all the i's together have to be equal to 0, all the j's together have to be equal to 0, and all the k's together have to be equal to 0. By knowing this, you can build 3 equations and you have 3 variables, and you can just solve them. So let's add all the i's together. You know that -0.308 AB plus 0.286 AC is equal to 0. This is I plus I. We got our first formula. Let's add the j's together. Minus 0.923 AB minus 0.857 AC plus 0.923 dA is equal to 0. And this is our second formula. Now our third formula, all the k's together. 0.231 AB plus 0.429 AC plus 0.385 dA minus 400 is equal to 0. And I can just pass the 400 to the other side, make it a little simpler. Let's say 0.231 AB plus 0.429 AC plus 0.385 dA is equal to 400. So as you can see, we have 3 equations: equation 1, equation 2, equation 3, and we got 3 variables, so this system can easily be solved. So let me turn the page. I'm trying to stay neat, because you guys gotta understand, in your paper as you're copying this exercise that I'm doing, please be neat. Otherwise, like I said, you mess up a little sign, you mess up the whole thing. So I wrote the numbers for the equations, and I'm going to show you what I'm doing to them to solve them. But this is basic algebra. From here on, you should be able to solve them on your own. Equation 2, I'm going to divide it by 0.923. And when you do, you get this equation. Minus I'm doing AB. Minus AB minus 0.928 AC plus dA is equal to 0. Now equation 3, I'm going to divide it by minus 0.385, and I get -0.6 AB minus 1.11 AC minus dA is equal to -1039. So when you add them together, as you see, the dA's cancel out, and I get this new equation, which is minus 1.6 AB minus 2.038 AC is equal to -1039. So the next thing that you do, let me go back to this equation 1 right here. From equation 1, you can basically solve for AC, and you get AC is equal to 1.066 AB. And I'm going to call this equation 4. Let me go back. So I'm going to plug in equation 4 into here. So I'm going to plug in 1.066 AB right here in AC, and I'm going to get this new equation, which says minus 1.6 AB minus 2.173 AB is equal to negative 1039. So you add this together, you get AB something, you divide it by negative 1039, you get AB is equal to 275.4 pounds. And now that you got one, we can easily find another one just by plugging in, for example, you plug in this AB value into this formula right here, you solve for AC, and you get that AC is equal to 298.6 pounds. You can go ahead and keep plugging this in into other equations to find the tension on dA. You could plug this 2 into this formula, for example, right here, and you will find it, but they're not really asking you for dA. Let me see. Determine the tension developed by the cables AB and AC, and oh yeah, they actually want the force on AD, so let me actually find it. And AD, when you plug it into when you plug these two values into, let's say, this formula right here, you get that AD is equal to 552.6 pounds, just about. So final answer, final answer. Please comment below if you want me to do any problems, and I'll be happy to help. Thank you.